Today we're going to talk about section 5.7, which is about roots and zeros. And prior to this, for the last little while here, we've been working with different polynomial equations, and we've been factoring them is what we first started out doing and breaking them apart into their different pieces. And then eventually we went to solving different polynomial equations. And we did it by factoring was one way. We did the quadratic formula to help us solve quadratic equations and completing a square and factoring, like I said. So we've been taking a look at different ways to solve these things. Okay, and we've been trying to find the different solutions. Okay, and when we talk about a solution to an equation, we're talking about the value of x. What can x equal? Well, another word for the solutions are the zeros. Okay, and if you remember when we factored things into like x plus 3 and x minus 2, we were trying to find the value of x that made each one of these equal to 0. Okay, and when I did it, I'd get -3 and I'd get, positive 2. Okay, but these answers down here, the solutions as we call them, they also have a special name called the zeros. Okay, and they're also called the roots. So when they talk about solutions, roots, and zeros, we're all talking about the same thing here. We're trying to find the value of x that makes that equation true. Okay, now when we've been solving these, we once upon a time I think we had to classify and tell how many and which kind of solutions there were. Okay, and at the time there, when we did that, we had two kinds of solutions. We had real solutions. Okay, and those are the ones that are like your regular numbers, x equals 2 and 3 and 5/4. They could be fractions and decimals. Okay, but that's the majority of the ones that we had. And then we had these other ones over here called imaginary solutions. Okay, if you remember, the imaginary solutions were the ones where we had i's in our answers, where we had a square root of a negative number. But these are the ones that had i's in the answer. Okay? So when we solved our equations prior to this, our answers, our zeros, had to fall into one of those two categories. Well, there's actually another, these two things are actually part of a bigger number system called the complex numbers. Okay, so all the numbers, think of it kind of like the universe, all the numbers out there in the whole entire universe belong to the set of complex numbers. And of the complex numbers, they can be broken apart into the real numbers, the real solutions, and the imaginary solutions. Okay, and we're going to talk about a couple of things that we've mentioned here over the last several lessons. Okay, the first thing here is this thing called the fundamental theorem of algebra. And basically what this says, if a polynomial has a degree greater than 0, okay, so if I have an x to the first power, an x to the third power, an x to the fourth power, anything where we have a variable that has an exponent greater than 0, it's going to have a solution, it's going to have a root, it's going to have an answer that's part of the complex numbers. Okay, it's either going to have some real solutions or imaginary solutions. Okay, but this is the really important one that we're going to take a look at. Okay, we've kind of mentioned this before, a corollary to the fundamental theorem, so it's kind of like an extension of that. Says that if a polynomial has degree of n, then it has n roots in the set of complex numbers. And this we mentioned a while back. Okay, and I've kind of hinted at it a little bit. If I have something that has a degree of 3, if the largest exponent is a 3, then it's going to have 3 solutions. Okay? If it has a degree of 4, it's going to have 4 solutions. A degree of 5, it's 5 solutions. And what we looked at a while back was we said that if it is an even number, if the degree is an even number, that's the maximum number of solutions it could have. So this could have 4 solutions, but it could also have 2, and it could also have 0. Okay? But an even number. And if it had, let's say the 5th power, it could have 5 solutions, 3 solutions, or 1 solution. Any odd number less than 5, it could have that number of solutions. Okay? Yeah. And one thing to make note of here, it talks about repeated roots. So and we'll see here shortly, in a minute, that if a number repeats itself, like if it has a solution of x equals 3, another x equals 3, and x equals 5, it counts the 2 3s as separate ones. So even though they repeat, they're going to be counted. Okay? Here's one of these. So here they have an equation up here, x squared plus 6x plus 9 equals 0. Okay? And then we're going to solve it. Now they didn't show it here, but this actually factors into x plus 3 and x plus 3 equals 0. they wrote it as x plus 3 squared. Okay? But if I was to solve this, and if I use my little shortcut, and remember it's just the opposite of whatever's in the parentheses, I get two negative 3's. Okay? But the corollary says that if it has a degree of 2, it's a second power, it should have two solutions. And it does. 1, 2. They just happen to be the same. So it looks like 1, but really there's 2. And what I want to point out here is the repeats count separately. If that makes sense. Okay? And it's what's called a double root. Okay? So it has, if I was to really classify this, how many answers does it have? Okay? It has two solutions. It happens to be the same solution, but these would be two real solutions. Okay? It's just a double. It's the same number. Okay? All right, here's another one. If I look at this one, x cubed plus 25x. Okay, what they did here is they factored out an x out of each one. Okay? And when we have an x factored out in front, 0 is a solution. And then they looked at the second part here. Now that does not factor into x plus 5 and x minus 5. That only happens with perfect squares when it's subtraction in between them. This one has addition. So kind of what they did here is they took this stuff, they set it equal to 0, subtracted 25, and then they square rooted both sides. And the most important thing here to remember is, remember when you square root both sides, you always have to introduce the plus and the minus. Okay, when you do the square root of 25, negative 25, it's plus or minus 5i. Okay, and according to that corollary, I see it was an x to the third power. I should get 3 solutions. Well, did we get 3 solutions? Yep, we had one of them right here. X equals 0 is a solution. And then there's 2 of them here for a total of 3 solutions. Okay? And these would be, if I wanted to classify it, it would be one real solution, and this would be 2 imaginary solutions. Okay? One real root, 2 imaginary roots. Okay, and so this is going to be kind of just a little extension. We've done most of this before. Okay, and we're going to classify them when we're done here. We're not going to worry about graphing them today. Okay, but by the way, speaking of the graph, if you were to graph this equation, the graphs are only going to show the real solutions. Okay, the graph does not show imaginary solutions. Okay, so we kind of have to do it out algebraically to find them all. Okay, so we're going to practice a few here. Okay, how about this one? Very similar to the last one. Before I even start here, I see x to the third power. So in my mind, I'm thinking I should get 3 solutions. I want to find them and then tell me how many of each kind I have. Okay? Most of what we're going to do here when we solve these is going to be done by factoring. And the very first thing we want to do when I factor things is I want to see, is there a greatest common factor? Okay, and there is. If you notice, both of these have an x in common. So I'm going to take out an x. And if I do that, I get x squared plus 2. Okay? When I do that, I always look at that leftover stuff and I'm thinking, well, can I factor that? I want to try and factor it, but it's not factorable. Okay? And this guy obviously is its own term. Well, I have one solution. Whenever we have an x factored out in front, 0 is a solution. And it actually doesn't matter if it's an x squared, an x cubed, an x to the 4th. If there's an x out there, 0 is one of them. Okay? And then how about this one? How do I find the solution to that if it's not factorable? Well, let's set it equal to 0. X squared plus 2 equals 0. And let's try and solve for x. Just like the last one we saw. If I subtract 2, x squared equals negative 2. And then to get rid of the square, I square root both sides. And whenever I do that, before I even look what's over there, I always write plus or minus. Okay, and what do I have the square root of? The square root of negative 2. Well, negative 2 is not a perfect square. It can't be simplified. It doesn't have any other factors. So it's just going to stay the square root of 2. But the fact that it's negative means there's going to be an I in my answer. Okay? And just like that, did I get the 3 answers? Did I get the 3 solutions? 1, 2, 3. Yep. Okay, and this is 1, and if I had to classify, maybe I'll write it right here. I have 1 real solution and 2 imaginary solutions. Okay? And on your assignment today, make sure you tell how many of each kind. 1 real, 2 imaginary. Okay, so again, that was a little factoring problem. Factoring out the greatest common factor and then solving. Okay, how about this one? Okay, now There's nothing that goes into both of them. They don't have a greatest common factor. And I see x to the fourth. And then I see 16. Okay? Well, they're not perfect cubes, but are they perfect squares? Is there just two terms? Are they being separated by subtraction? I think so. Okay? So how does this work? They're actually perfect squares. And if you remember from a while ago, when I see x to the fourth, x to the fourth always breaks apart into x squared and x squared. 16 is a perfect square also. The square root of 16 is 4. And then the signs on these perfect squares, one is plus and one is minus. Okay? Now how do I solve that? Okay? If you look close, there's a couple different ways to do this. If I look at this one, x squared minus 4, I could actually factor it one more time. These are perfect squares. I could use that same rule. I could do x and x. The square root of 4 is 2. 1 is plus, 1 is minus. And if I use my little solving technique for things that are factored, this one is negative 2. And this one is, this one is positive 2. And I'm kind of using my little shortcut, but I could set each of those equal to 0 and solve them. Okay? But the reason, the reason I could factor those is because it was subtraction, just like this guy. Can I do the same thing over here? No. They're perfect squares, but I can't do it with addition. So how do I do this one then? Well, what I do here is I'm going to do what I did in the last problem. I'm just going to set it equal to 0 and solve it. Let's solve it algebraically. What if I subtract 4? X squared equals negative 4. If I square root both sides, they cancel out. I get plus or minus, and I get the plus or minus square root of negative 4. Well, the square root of 4 is 2. And because it's negative, it's going to have an I in it. Okay? And there we have it. And again, if I go back to that fundamental theorem or the corollary, actually, if I have a fourth power, I should get 4 solutions. Did I get 4 solutions? 1, 2, 3, 4. And there they are. And if I had to tell how many of each kind, these two guys right down here are the 2 real solutions. And this is the 2 imaginary solutions for a total of 4. Okay? So, yep, we're going to continue to do some of this factoring stuff that we've done over the previous couple lessons. There's not a whole lot of new business with that. Okay, so there's one that had perfect squares. I got a couple more here for us. Oh boy, how about this one? If you look carefully there, how many terms are there? 1, 2, 3, 4. And a while back, a couple different times now, we've talked about a method that's used to solve when there are 4 terms to a polynomial equation. Remember what that is? There's a name for it. It starts with G, and it was called grouping. Okay? And the way that grouping worked is we grouped the first 2 numbers and the last 2 numbers. And the one thing I had to check for with grouping is, what if there was a minus sign in between those? If there was a minus sign, I changed the last one. But this is plus, so we're good. Okay? Then the way that it works here is we look for a greatest common factor out of the first group. If you look closely there, each of those have an x squared in it. And if I do that, I get a 3x minus 1. And notice it's a 1 left over, not a 0, because I have to be able to distribute back through, but there's a 1. I look at the second one here. Is there something that these two guys have in common? I think they have a 3 in common. So I'm going to factor out a 3. And I get 3x minus 1 left over there as well. Okay? And if you remember with grouping, the thing we're looking for with grouping is we're looking for a common expression that they have in common. And you can see that both of those have a 3x minus 1 in common. So I'm going to factor that out. I'm going to take that away from each of those. My 0. And see what's left over. If you see what's left over, I have an x squared plus 3. Okay? And I always kind of check this leftover stuff. Is that factorable? Can we break that apart into 2 parentheses any further? No, I don't think so. They're not perfect squares. And by the way, it's addition, so we're kind of stuck. Okay, so I got it partially factored. How am I going to find the solutions to this? Okay, well, I can set each one equal to 0. Some of you might even be able to use a shortcut here. The solution here would be positive 1 divided by 3, positive 1/3. But if you don't see that, just set it equal to 0. Then if you add 1 and then divide by 3, there's 1/3. Okay? And over here, if I do this one and set it equal to 0, if I subtract 3, I want to get rid of the square, so I'm going to square root, plus or minus. The square root of 3 is not a nice number, but it's negative, so it's going to have an I in it. So you get something that looks like that. Okay? Plus or minus I square roots of 3. And just as a double check, I should have maybe did this beforehand, but if I go back to the very beginning here, what was the degree of this polynomial? It has a degree of 3, which tells me I should get 3 solutions, or 3 roots, 3 zeros. And did I get 3? Yes, I did, down there at the bottom. Oops. Okay, and if I classify them, okay, this is 1 real solution, and this again is 2 imaginary solutions. Okay, for a total of 3. But again, all this factoring stuff we've done before. The one new thing that might be is finding the solutions of this part. But we just set them equal to 0 and solve. Okay? How about this one? This one's a different one yet. Okay? And maybe you recognize that one as being one of these perfect cubes. Okay, and here's this from the other day also. Do you remember how to factor perfect cubes? Well, 27 is a perfect cube. The cube root of 27 is 3. And 8 is also a perfect cube. The cube root of 8 is 2. Okay, so what I do when I factor perfect cubes, if you remember, I have a small part, the short piece, and then the big piece. The short piece comes from taking the cube root of each of those. And the cube root of 27 is 3. It'd be a 3x. And the cube root of 8 is 2. Okay? And once we get this first piece, I guess I'm down here, we use that to make the second part. Okay, and you remember the first number in this second parentheses comes from the square of that, which is going to be 9x squared. I change the sign, that becomes plus, and then I multiply the two together, that's going to be 6x. And the last number comes from the square of the last number, which is 4. Okay? And there I have it factored. And I need to find my solutions. And this time, right away here, I see an x to the third, so I should get 3 solutions. Okay, let's try this once. And I'm going to maybe use my shortcut. I'm hoping some of you guys can kind of see this. This should be a positive 2 divided by 3. Positive 2/3. Okay, and if you didn't quite see that, set it equal to 0. 3x minus 2 equals 0. Add your 2 and divide by 3. X equals 2/3. But the more and more of these that we do, okay, if it's just a little binomial like this, the opposite of the last number divided by the first number. Okay, now what about this? If you remember from previous lessons here, we talked about the second part of this perfect cube part. It's not factorable. It's never factorable. Okay, well, so then what? How do you solve this? Okay, well, this leftover piece is always going to be a second power. It's going to be a quadratic. Okay, and the way that you have to solve the other part, the second part of this, is we have to use the quadratic formula. Okay, and we did some work with a couple different times with the quadratic formula. Okay, and let's give it a whirl here. Okay, so let's see, maybe I'll write A is going to be 9, B is 6, and C is 4. So let's try the quadratic formula. If you remember, it's the opposite of B, so negative 6, plus or minus the square root of B squared. 6 squared is 36, minus 4AC, 4 times 9 times 4, all over 2A. And 2 times 9 is 18. Okay, so for the second part of this, unfortunately, there's a little bit of work to it when we use the quadratic formula. Okay, and like I said many times before, when we do the quadratic formula, let's use our calculator and simplify that part of it. Square root of something over 18. Okay, and if I pick up my calculator here, I'm going to do 36 minus 4 times 9 times 4, and I think I get negative 108. We've seen this number a couple different times. Okay, and then let's look at that number, negative 108. Is it a perfect square? No, it's not. Okay, but it can be simplified. Okay, and if you simplify it, if you looked at on your factor sheet, the two black ones are 36 and 3. And we know the square root of 36 is 6. Okay, so I can simplify this one more time. The square root of 108 is going to turn into a plus or minus 6, and because it's negative, it's going to have an I with the square root of 3 all over 18. Okay, and last but not least, I think I can simplify that one more time, because I think there's something that goes into all three of the big numbers there. And what goes into all three of those big numbers? A 6 does. And if I divide out a 6, I get a negative 1. That goes away, and that turns into a 3. So I get negative 1 plus or minus I square roots of 3 all over 3. Okay? Yep. And so just to count my answers here, this looks like it's two imaginary solutions because they have the I in it. So there's two imaginary. And if I scooch up a little bit here, my other one right here, this was one real solution. One real, two imaginaries, for a total of 3 solutions. Okay? So there's one with a perfect cube. We saw perfect squares, we saw perfect cubes, we saw take out a greatest common factor. Okay? And how about one last one here? Yes. One more. Now this one's a little bit different as well. Okay? An x to the 5th power. When I look at this x to the 5th power, this tells me I should get 5 solutions. 5 of them. Okay, well man, how do I do that? Have we factored fifths before? Nope. Okay, there's 3 terms, so I'm going to, that's not what I do. Well, if I'm kind of stuck, the very first thing I always look for is a greatest common factor. And is there something that goes into all 3 of those terms? They don't have any numbers in common, but they all have an x in common. So I'm going to take out an x. And when I take one x away, I get x to the 4th, 2x squared, and then I get plus 1. Okay? And I'm going to look at this leftover stuff, and I'm going to try, is that factorable? Okay, I think it is. Watch this. X to the 4th can be x squared and x squared. And what about the factors of 1? The only factors of 1 are 1 and 1, and can we use them to get a 2? I think so. What if I put a 1 there and a 1 there? I get 1x squared and 1x squared. If they're both pluses, I get 2x squared. Yeah. And I'm just going to drop this x down here. So now I'm sitting with that. Okay? And I want to find its solutions. Okay, well I think there's one of them staring at me right here when I have an x factored out in front. X equals 0 is a solution. Okay? Now if I look at both of these, some people might think x plus 1 and x minus 1. Some of you are thinking that they're perfect squares. But remember, perfect squares only works when it's subtraction in between them. These have addition, so they're not factorable. Okay, but well, if they're not factorable, what can I do then? Well, I can set each one equal to 0. X squared plus 1 equals 0, and x squared plus 1 equals 0. We're going to get the same answer. But if I subtract 1 and square root, the square root of negative 1 is I. And the same thing's going to happen over here. If I square root, I get x equals plus or minus I. Okay, so I get a couple repeats. There's one where that's a double root. Okay, but let's see. Can we count 5 of them? Well, there's 1, 2, 3, 4, 5. Okay, and so if I wanted to classify these, this would be my one real, and this is 1, 2, 3, 4 imaginary solutions. And even though they repeat, okay, let's pretend, let's count them all as separate ones. Okay, even though there's really only 2 different imaginary solutions, the plus I and the minus I. Because they repeat, let's still count them so that we can add up to a total of 5. Okay? So again, a lot of what we've done here so far has been very, very similar to what we've done in the past. We're just kind of putting all the pieces together here. But the factoring and the solving are the 2 parts to it. Okay? All right, there's one last piece to this rather. We're going to go backwards. Okay, and we saw this on the first test that we did a while ago. is I gave you a couple solutions, and I wanted to know the equation that they came from. Okay? And one thing that a few people did wrong, or didn't quite get on the last test, it wants it in standard form. If you remember standard form, there's no fractions. Okay? And it goes in order from x squared, x to the first, or it goes from the biggest exponent to the smallest exponent. Okay? Well, how are we going to do this? Okay, what if I told you these were the three solutions? I want to find the polynomial equation that they came from. Well, this is doing that factoring business in reverse. Okay? And if you remember, if I said x equals 5 as a solution, okay? Okay, if I go way at the very end and I said x equals 5, x equals -3, and x equals 1. If I had things factored, where did that come from? Well, x equals 5 came from x minus 5, if you remember. X equals -3 came from x plus 3, and x equals +1 came from -1. Remember, it's the opposite of what it looks like. Okay? So rather than working our way down and factoring and getting to our solutions, we're going to start with our solutions and work our way backwards. Okay? So once we get our parentheses, to find the polynomial, we just have to multiply all that together. We're going to FOIL it to start with. I have three things. How many things can you multiply at a time? We can only multiply 2 at a time. And it doesn't matter which 2, but I'm going to do the first 2. So I'm going to start there. And I'm going to FOIL those pieces together. I'm going to move up here. Okay? And if I FOIL, I'm going to get x squared plus 3x minus 5x minus 15. I'm going to do this kind of fast. If I combine my middle terms, that's minus 2x minus 15. Now that's what I get when I multiply the first 2 together. I now have to take that times the third one, x minus 1. And I'm going to multiply that together. Okay, it's really just more foiling, to be honest with you. If I go here, I get x cubed minus x squared. Then I'm going to take that one through, minus 2x squared plus 2x. Oops, this isn't, yeah, it is. Okay. And then I'm going to take the 15 through, minus 15x plus 15. Okay. And then last but not least, I just have to combine my like terms. Okay, and I said standard form, so we want the biggest power to come first. Well, there is only one x cubed. That's the biggest one. So that one's done. I see a couple x squareds. -1 minus 2 is -3x squared. They're done. These two are like terms. 2 minus 15 is -13x. And then plus 15. And there's my answer. Okay? So in my opinion, the tricky part of this, the most important part, is getting started. If you know what the solutions are, okay, they just come from, oops, that one there and that one there. They just come from the opposite of what they look like. Okay? All right, here's the last one. Okay? So the difference with this one, there's my 2 real solutions. Well, now I have a 3i. Okay? How does that differ? How does that come into play? Well, let's start out here. If 3 was a solution, it comes from x minus 3. Again, we start out by doing the opposite. If -2 is a solution, it comes from x plus 2. Oops. Okay. Oh. X plus 2. Now, how about the i's? Now, if you remember, where does an I come from? Okay, it comes from when we had the x squared equals something over here, and it was a negative number. And I square rooted, and I always get a plus and a minus. Okay, so the trick here with these i's, okay, the i's actually come from 2 places because it has 2 solutions, a positive and a negative when we do the square root to both sides. So when we do the i's, one comes from x minus 3i, and one comes from x plus 3i. So technically there's a plus and a minus out there that they kind of omit, but it actually comes from 2 places. Okay? So just so we're all crystal clear on that, when you do the i's, it actually comes from 2 solutions. Okay? Now, holy mackerel, now we got to multiply all that stuff together. Well, again, like on the last one, we can only do 2 things at a time. Okay? So I'm going to multiply the first 2 together, and then we'll do the second 2. Well, if I multiply the first 2 together in FOIL, I'm going to get x squared plus 2x minus 3x minus 6 2 minus 3 is negative 1. So that's what I get with my first half of the polynomial. How about in the second part, the right side over here? Now, if you remember, there's a special name for these things. They're called conjugates. Okay, and there was something special that happened with the conjugates, as we'll see here. There's x squared, but I get a plus 3xi and a minus 3xi. Okay, when I do those middle terms, what happens with the positive and a negative 3xi? They cancel each other out. Okay, but I still have one more term to go. And this is the tricky part. Negative 3i times positive 3i. Well, a negative 3 times a positive 3 looks like it's negative 9. But if you remember, anytime we multiply an I times an I, it's negative 1. So it changes the sign and makes it become positive 9. So down here I get x squared plus 9 for my product of those 2. Okay? And notice the i's disappeared. The i's should disappear when we multiply these. Okay? And lastly here, to find my big polynomial, I need to multiply all of that together. Okay, and we're going to get kind of a big long polynomial expression here. Okay? How's this go? So I'm going to go the x, I'm going to take that and distribute it through. I'm going to get x to the 4th plus 9x squared. Then I'm going to take this negative x and distribute it through. I'm going to get negative x cubed minus 9x. And then I'm going to take the 6 and multiply it through. Negative 6x squared minus 54. Okay? And then I'm going to combine my like terms. And again, for standard form, I want the biggest one first. Well, the biggest power I see is x to the 4th. That's done. The next one I see is a negative x cubed. It's the only x cubed. Okay? I see a couple x squareds. 9 minus 6 is plus 3x squared. Minus 9x right there, and then minus 54. And I get a 4th degree polynomial. Okay? But once again, it all starts from the very beginning here when we're finding these, trying to find the polynomial equation. It starts with the opposite. Positive 3 came from minus 3. Minus 2 came from plus 2. And the i's always have 2 solutions. Okay? There we have it. In a minute here, there's no new assignment for tomorrow, okay, as far as doing on your own. In a minute here, when you shut this off, click down on the next video, and that's one that we're going to do together for your homework assignment. It's more just the same as this. Thanks for tuning in.